Welcome to lesson 6.1, the exponential function and its inverse. Just as a little bit of a warm-up, I'd like you to be able to identify which of these is a linear, which of these is a quadratic, and which of these is an exponential function. Why don't you take a second now, see if you can label them. And if you're able to label them, why don't you see if you can come up with the general equation that we use for each of these functions. You should be fairly familiar with them. Okay, so hopefully you were able to identify this line as a linear function, this parabola as a quadratic function, leaving this swoop as an exponential function. And the basic formula for these, hopefully we remember from our early algebra days, y equals ax plus b, or some write it as y equals ax plus c because we like to use c to mean the constant. Then we have the quadratic, y equals ax squared plus bx plus c, again where c is the constant and the highest power involved, the highest power of x involved in the quadratic is x raised to the power of 2. And today we will be working with these exponential functions. The general equation for them is y equals some base raised to the power of x, where the variable now is in the exponent, which is different from the quadratic or the linear function. Okay, before we get into the bulk of our lesson, a few more notes on the basics of exponential functions. These are going to be things that we need to be able to identify quickly and easily. So here we have an example. When we have an exponent, a function that has y, and the base is a whole number, and we raise this to the power of x, this is going to result in growth. Okay, and we can sketch that out. Anytime we have the value of x, as x gets greater, and I'm raising a whole number, say the number 3, to the power of x, then clearly as x increases, y is going to increase. This is an example of exponential growth. Okay, next we have an example of exponential decay. So we have the same basic formula. We're going to have y, where the base is a whole number, and we're going to raise it to a negative exponent. This is going to result in a model for decay. And now, every time x gets bigger and bigger and bigger, we know that this is going to get flipped. This is going to be the reciprocal. We're going to have the whole number squared in the denominator. So what's going to happen here is we're actually going to get smaller and smaller and smaller and smaller. It's going to be a decay model. So here we go. Decay. Something else we need to know. When we have an exponential function where the base is a fraction or a decimal, so that's anything between 0 and 1, and it's positive, we're raising it to a positive exponent, this too will result in decay. And so our decay graph, again, looks like this. The last one we have here, when we still have the base, which is a fraction or a decimal, and we're going to raise it to a negative power of x, well now it's going to do the opposite of what it was doing above, because we're going to be able to move the exponent into the denominator. Now what we have is a growth model for growth. A few basics that we need to be able to remember and recall. one final note on exponential function basics. Here we have the comparison between an exponential function with a base that is greater than 1 and another function with the base that is between 0 and 1. So here we have on the left, we have a function that is y equals b to the power of x, where b is greater than 1. Again, a growth model. On the right, we have the graph y equals b to the power of x, where b is greater than 0 but less than 1. It is a fraction or a decimal. And this is, again, a decay model. Moving on to example 1. Example 1, we're going to write an equation to fit the data. So the first thing I want to do here, just like you've probably done before, we want to take the first difference of these values. So I'm going to find the difference between what happens at x equals 1 and what happens at x equals 0. So all I have to do is go 4, take away 1. The first difference here is 3. 16, take away 4. The first difference here is 12. 64, take away 16. The first difference here is 48. Now I don't see a constant happening here. I could go ahead and take my second difference. I don't need to. That would tell me that it was indeed quadratic if the second difference was the same. But I see something already. I see that the difference here, the first difference, is raising from 3 to 12, from 12 to 48, proportional to the increase that I see already in y, from 1 to 4, from 4 to 16, from 16 to 64, which tells me that there is a ratio, there's a common ratio that these are increasing at. And I can show you what that means. If I take the difference, if I take the ratio between, let's say, 4 and 16, well, it turns out that that's the same as the ratio as between 3 and 12. It's also the same as the ratio between 16 and 64 and between 12 and 48. So you can see there's a common ratio. Each time I go from one value of y to the next, I'm simply multiplying by 4. So because y is increasing at a rate proportional to the function must be exponential, which means that my equation is going to be in the form y equals b to the power of x. So now I simply need to substitute some of the given values to find out what b is. Well, I'll try my first one. I'll sub in x equals 0 and y equals 1. So y equals 1, x equals 0. This statement is true for any value of b because any number raised to the power of 0 is equal to 1. So it doesn't give me any helpful information. So I'll try another one. Y equals 4, and it's b to the power of 1. Well, the only possible value here for b is going to be 4. We can show that this is the same as saying 4 to the power of 1 equals b to the power of 1, and b equals, slide that up, 4. So now I know that b is 4, so my equation becomes y equals 4 to the power of x. And I want to check that out just to make sure with another one of my values. So I'm going to go ahead and see if that's true. I'll sub in 16 for y and 2 for x. And I see that, yes, indeed, 4 squared is equal to 16. So the equation for a function that fits the data in the table is y equals 4 to the power of x, an exponential function. Okay, in investigation 2, we are going to do some work in discovering the nature of the inverse of an exponential function. So we have here the exponential function that we'll be working with, y equals 2 to the power of x. And we're first going to find out what would happen, where would we plot this graph for y equals 2 to the power of x. In order to do that, we're going to be filling in a chart. I'm just going to get it started, and then I'm going to leave you to it. And ... your chart will go all the way to x equals 4. So I want to find the value of y at these points. Well, 2 to the power of negative 4 is 1 over 16. Well, the y value here is 16. If we were going to plot the graph of y equals 2 to the power of x, it would run through the point negative 4, 16. Where are we when we plug in the value of x equals negative 3? Well, we're at 1/8. X equals negative 2, 1 over 4. And you're going to continue that chart all the way down until you get to y equals 2 to the power of 4, which is of course 16. You can put all your y values in the column for y value. And we're not actually going to have to work with y equals 2 to the power of x. We want to see what happens to its inverse. And all that happens when we take an inverse is we are swapping the x and the y values. So after doing the work, it's quite easy to see. The inverse function of y equals 2x is going to run through the point 16, negative 4. It's going to run through the point 1 over 16, negative 4. It's going to run through the point 1/8, negative 3. It's going to run through the point 1/4, negative 2. And you'll finish your chart and come all the way down here to the point 16, 4. Okay, after completing that table, you'll use the information that you found to sketch the graph of y equals 2x, which is the original function that we started with. You'll also graph its inverse, which, if we just switch the place of x and y, is x equals 2 to the power of y. And you'll also graph the line y equals x. And what you need to record is the key information for each of these functions, not the line y equals x. The line y equals x is just to show you that the inverse is reflected over y equals x. But you're going to state the domain and range, the x-intercept if it exists, the y-intercept if it exists, the intervals for which the function is positive and intervals for which it is negative, also intervals for which the function is increasing, intervals for which it is decreasing, and an equation of the asymptote. You can find all of that, a guide to finding that key information is on page 314 under Investigation 2. You're going to sketch it in your notebook, identify the key information, and then compare the two, see if you can note any differences or similarities. Okay, the work that you did in Investigation 2 will be confirmed in Example 2, where we compare the key features of an exponential graph and its inverse. And the exponential graph that we are working with here is the function y equals 4 plus x, and its inverse x equals 4 to the power of y. We want to identify this key information, and I'm just going to work through this chart. I've already drawn my little graph here with both of them. I also have the line y equals x, just to show us that it is flipped over the line y equals x. So the domain for y equals 4 to the power of x, simply x element of the real. There's no restriction there. Range, y element of the real, and we can see y is always greater than 0. X-intercept, well, it's never going to cross the x-intercept, the x-axis, so none. Y-intercept occurs when x equals 0, so y equals 1. Positive intervals, well, we just said that the range is all of y, but y always greater than 0, so the whole thing is positive. It's positive for all values of x. Negative intervals, none. Increasing, we can see it is increasing for all values of x, and it is never decreasing. And the the asymptote occurs at y equals 0. Hopefully we can see that on the screen. Okay, switching over to our inverse function, x equals 4 to the power of y. Domain, again, there is no restriction on x except, what do we notice here? X is never negative. It never reaches 0. So here we have x element of the real, and x, is greater than 0. And the range, there is no restriction on the range. Y element of the real. X-intercept, there is an x-intercept. It occurs at x equals 1. There is no y-intercept, and I hope, none. I hope that we are starting to see a pattern here between the domain and range of these two functions, as well as the x and y intercepts for these two functions. Let's see if that pattern continues. We're looking at positive intervals. Well, it's positive when x is greater than 1. It is negative for x less than 1. Increasing. It's increasing for all values of x. Decreasing? Nope. No intervals. And the asymptote occurs at x equals 0. There is no horizontal asymptote. All right, some homework for you to try to apply your new skills using exponential functions and their inverse. 6.1, page 318, numbers 1 through 10.